The objective of this video is to introduce multi-objective optimization of AC machines using population-based optimization algorithms. That's a mouthful. That's a lot of technical terms there. Let's slowly unpack this through this video, and I want to start with a high-level overview of what we are doing when we are optimizing a machine design. We'll draw this as a flow diagram. And so any design process begins with a design specification. And for an AC machine, a design specification will typically be a rated speed, a rated torque or rated power, perhaps a certain voltage or current requirement. Maybe there might be some constraints on the form factor or the size of the design, and then a definition of what the objectives are. So whether we're trying to minimize losses, we're trying to minimize the size, so on. So we need to have a design specification from our customer, from the application that we are creating a motor for. And from this design specification, we can construct an initial design of a motor. And our ability to construct an accurate initial design is critical to our ability to optimize our motor. We use our initial design as kind of a hybrid of our optimization problem formulation and as a template for what we expect our final design to look like. So the better job that we can do in determining what the parameters of our design should be, the more likely we're going to have a successful outcome of our optimization. And what all is involved in this initial design? Well, we need to select a winding layout, so we need to determine our slots, poles, and phases, and we want to determine a winding layout that's going to give us a good outcome for our final design. So we've talked previously about how some windings have better winding factor than other windings, and we want a design here with a good winding factor for our objectives. So that is, if we want really low torque ripple, you're going to want to have a winding design that has lower harmonics at higher frequencies. Or if you want to have a design that has really high power density, you're going to want to have a winding layout that has a very high fundamental winding factor. And then that second bullet point, the parameterizing geometry, that is coming up with a reasonable set of parameters that we can specify to fully define our design. So in one of our homeworks, we gave you a cross-section of the motor with a bunch of dimensions labeled on it. When you do this initial design step, you're going to pick which of those dimensions are variables that your optimization algorithm is allowed to change. And if you have all of them being variables, you'll end up with a very broad design space. That means you have so many variables that there are so many combinations of variables that could define your design that it's hard to converge to a design that performs well because there's just too many combinations out there. You know, if you have 13 or 14 variables, you're talking about a huge design space. And so your goal here is to try to come up with a set of parameters that your optimization algorithm is allowed to vary that is relatively small. So the fewer parameters you have, the smaller your design space is, and the easier it is to find a design that is optimal, that's the best. And then finally, this business of determining design constraints. Well, you know right off the bat that you have some minimum and maximum values for a lot of your parameters. Maybe your air gap, you only want it to range from 0.5 millimeters up to 3 millimeters. And so this is the time when you want to list those out and specify them. Our next step is that we need to convert our initial design to a set of performance metrics. So that is, we're going to evaluate our design and determine how effective it is at meeting our design objectives. And typically we'll do this using either finite element analysis or a magnetic equivalent circuit, or maybe the direct solution to the fields. And it depends which approach you take, depends on how accurate you want to be versus how quick you want to be. And sometimes you might take a hybrid of all of these approaches to try to get the best compromise of accuracy and speed. And so in our homework, we'll be doing this with finite element analysis. So you evaluate your design, you determine how effective it is at achieving your objectives, and then you decide if you are done, if you should stop your optimization process. So have you met your stopping criteria? If you have not, you're going to modify your design in some way, and then you'll go back and you'll evaluate your modified design. So where does our optimization algorithm fit into all of this? Our optimization algorithm guides this portion of the design optimization process. So that's an overview of our motor design optimization. We start with some kind of design specification, which is determined by the application that we're designing a motor for. We then construct an initial design, and we formulate the optimization problem. We then enter this loop where we're iteratively evaluating a design and revising the designs. And we do this until we've met some kind of stopping criteria. We'll talk about that more later. Now, what I want to do is move our discussion to talking about what our motor design space looks like and how that influences our choice of optimization algorithm. And the way that I want to talk about the motor design space is I want to create an example sketch or example plot of what an objective might look like when we vary a parameter. So remember, an objective is one of our design goals. So this will be, for example, the loss, or it could be torque ripple, or the design size. And I'm just speaking generically here. This is a hypothetical plot, but this is characteristic of what you could expect for your motor design. So consider that we're plotting one objective, whether this is loss or torque ripple or what have you, as a function of a parameter that we are varying. And the parameter is typically some geometric aspect. So maybe this is a function of our tooth width or our air gap length. And remember, this is just a hypothetical plot. And so what we'll find is that the motor design space is highly nonlinear and non-convex. What does that mean? That means that if we look at our objective function, it's going to look something like this. And you can see that this function, well, this is a particularly nasty function to try to optimize because we have all of these regions here which have what are referred to as local minima. So remember, we're trying to minimize this objective function. We've got one global minimum, which is down here, but we have all these things that my arrows are pointing to, which are local minima. And if we use conventional optimization methods, our methods will tend to get stuck in those local minimums. So our conventional mathematically based optimization algorithms, or gradient-based algorithms, struggle in this kind of design space. These are the typical algorithms that you'll learn if you take an optimization class. That includes Newton gradient descent, Newton's method, Gauss-Seidel, so on and so forth. So there's several of these kind of classical mathematical optimization techniques that have very well studied convergence properties and are very well understood and researched in the mathematics space that struggle a lot in this kind of design space where you have all these local minimum. And the reason is that all these algorithms are based off of calculating a derivative and deciding which way the algorithm should search based on that derivative. So if you calculate your derivative at this point in your objective function, it's going to tell you to pursue a path like this because the derivative is negative, so you know that you should move to the right to minimize. Now if you evaluate your design again right here, you can see that your derivative is positive, so you've missed your minimum, and it's going to tell you to go back this way. And you're going to ping pong back and forth until you reach a minimum. But this minimum is just a local minimum. The algorithm has no idea that there's a global minimum over here if it would just try to test a vector in this region over here. So all these algorithms in this kind of nonlinear, non-convex design space will converge to a local minimum based on where you start the algorithm off. If you were to start the algorithm with an initial design right here, it might ping pong like this, or depending on your design step size, it might shoot all the way over here, and then over here, and converge to this minimum. Or, if you pick the right design step size and the right starting point, you might actually reach the global minimum. But the point is that these algorithms, these kind of classic algorithms, tend to have challenges in this space. And for this reason, what's referred to as population-based algorithms are widely used. And population-based algorithms include genetic algorithms, differential evolution algorithms, there's algorithms called particle swarm optimization. So there's several algorithms, And these algorithms, most of them are loosely based off of some kind of biological inspiration. So they're typically not very heavily grounded in mathematics. They're instead grounded in they can also be called global search algorithms because they tend to try to search the entire design space, and they're stochastic. They have some randomness associated with them. They're constantly, if they evaluate a candidate design over here, they don't look at the derivative to determine which vector they should, which design they should investigate next. They might take the parameters that define this design and add some random variable, and then all of a sudden they're over here, or they're up over here. And so they don't always search in a direction that's immediately minimizing the objectives, but they have some logic in them to try to gravitate towards minimizing objectives while also adding some randomness to which designs that they evaluate. And for this reason, these optimization algorithms are very unpopular in design spaces that are well behaved. So if you have a design space that you could use a gradient-based algorithm, you would almost always use that because it has mathematical reasons for the direction that it searches. Whereas when you have these kind of design spaces where you have lots of local minimum, you typically have trouble using these gradient algorithms, and you're better off using some kind of global search algorithm which will randomly evaluate designs at different places and then selectively keep designs that perform or dominate other designs. And so we've talked about different concepts of optimization and multi-objective optimization. Let's now summarize the approach that we'll plan to take in our homework and design efforts in this class. And our approach is that we're going to define multiple objectives. And we're doing that because we acknowledge that in AC machine design, we inherently have multiple objectives. However, we're going to limit ourselves to 3 objectives or less so that we can reasonably construct and visualize our Pareto fronts. We're going to use an optimization algorithm to search for our Pareto front. And then when we construct our Pareto front, we will visualize the trade-offs and then use our design expertise, use our engineering knowledge to intelligently select a preferred design that we will call our optimized design. So what this means is that we are trying to construct this plot that I've sketched right here. We're going to define our objectives, and we'll use as few objectives as we can get away with. So we prefer to use 2 objectives because then this plot is easy to draw, but we can use 3 as well. And then we're going to use a population-based algorithm to search our design space in an effort to construct this Pareto front. And then when we construct the front, we'll plot it like I've done here, and we will intelligently decide which of these designs on the Pareto front, this is the Pareto front over here, we will intelligently decide which of these designs best meets our application. And so what I want to do now is talk through the high-level steps of a population-based algorithm, and then comment on the broader perspective of constraints we might place on this, and how we think about the objectives that we define. And so when we talk about the population-based algorithm, we're talking about what is going on in this space if we use a population-based algorithm. And remember, I've listed several examples of population algorithms. Each algorithm has its own preferred vocabulary. I'm going to be using as general as possible terms, and then you should be able to see how you could apply this using either a genetic algorithm or a differential evolution algorithm or a particle swarm algorithm. And we'll work through some of this in the homework assignment. The first step in your optimization algorithm is that it's going to construct an initial population. And a population is a set of designs that it's considering. These algorithms are called population-based because they operate on more than one design at a time. They'll consider a whole set of designs. And you typically fix the size of the designs you're setting. So I've labeled this as n here. So maybe you're going to use a value of n equals 50 population for your algorithm. That means that at every step in this process up here, you're actually performing this on 50 designs. You're maintaining a current list of 50 designs that you're evaluating and then modifying. And so this lends itself naturally to constructing a final set of Pareto designs if you maintain your population as just being the 50 designs that are on that Pareto front. And each of these designs is characterized by an array or a vector, which is a list of all the parameter designs that you're considering, which is a list of all the parameters that define your design. And remember, in our sketch of a motor cross-section, we had these different dimensions, and so this vector might be just a list of those dimensions. Or it might be some other, maybe you're considering those dimensions as being ratios of each other, then it'd be the ratios. So this kind of thing. But the point is that you have a vector that will describe each design, and that vector is a list of values of the parameters for a design. And second, your algorithm is going to evaluate the objectives of each design within its population, of each individual within the population. And the way it does this is it calls a function that you define. So if you're writing this in MATLAB, you will pass your optimization algorithm a function that it's going to call every time it evaluates an individual. And that function will typically do a finite element analysis and then post-processing to determine what the value is for the objective functions. So that is this step right here. Next, your optimization algorithm is going to sort the designs. And in a multi-objective optimization, where you are considering Pareto optimality, you do what's called a non-dominated sort. So you rank the designs, and your first rank is going to be a bunch of designs that are tied, that are Pareto optimal, that do not dominate any other designs. And then your lower ranks, further on down your list, are going to be designs that are dominated by preceding designs. So your first several designs are going to all be on your Pareto front that you've evaluated so far. So your Pareto front is constantly moving. Your design space has a true Pareto front. You just don't know it. You haven't evaluated enough designs to find out where your true Pareto front is. And so the first time you evaluate a set of designs, you figure out which designs do not dominate each other, and that becomes your Pareto front. Now you have some information, so you intelligently create a new set of designs. And when you evaluate those designs, then you discover that, oh, my Pareto front is actually closer over here. So now you think this is your Pareto front. But then you intelligently create a third round of designs, and now you discover your Pareto front might lie over here instead. And so you keep doing this, and your Pareto front continuously evolves until you converge to what is something close to the actual Pareto front, because you've evaluated enough designs that you can more definitively say where your Pareto front lies. So now, after you've ranked your designs, you figure out what your new generation of your population should be. And you do this based on the information that you've learned. So you take your best of your old designs, and then this is where the magic of your algorithm comes in. It somehow determines what the new generation should be. So it might retain all the Pareto designs from the old generation, and then perhaps it blends them with some of the less optimal designs, or perhaps it adds some random values to the parameters. And from this, you construct a new generation, and you go back to step 2 and you reevaluate your new generation. So you keep doing this loop over and over and over again until you reach a stopping criteria. So this loop is just a more detailed version of this loop, but described for a population-based algorithm. And the algorithm, again, is operating on a population, so you have this whole set of designs that you're constantly bringing along with you. You always have 50 designs that you're evaluating and then ranking, and then somehow you're combining these designs to construct a new generation that you will test. And so if you stop your algorithm at any given time, you can look at your current generation and construct a Pareto plot from it. And if your algorithm is configured properly, that Pareto front is constantly getting closer to the actual Pareto front. So the longer you run your algorithm, the closer you will be to converging to what the actual Pareto front of your design space is. And so the question then is, how many times should you go through this loop? What should your stopping criteria be? A very popular stopping criteria is just to put down a number of iterations that you go through the loop, how many times you will cycle the loop. Maybe you're going to have a population of 50 and you're going to go through this loop 100 times, or maybe 1,000 times. The more times you go through the loop, the closer you'll be to your actual Pareto front. Another approach to this is somehow defining a metric that quantifies how much your Pareto front moves between each iteration. And so if you notice that you're making only very small changes in where your Pareto front is located, that means you must be getting closer to the actual Pareto front. And maybe you decide that a change of such distance is small enough that you're happy and you're ready to exit your algorithm. This is quite a broad field of consideration of how you should stop your algorithms. For our case, we're going to consider the simplest thing, a number of iterations. So we'll just define how many times we want to go through our loop before we stop. So when we look at this set of steps that our algorithm is performing, I want to emphasize that we are users of the algorithms, we're not designers of the algorithms. So the perspective I want you to have when you're listening to this lecture and thinking about this is, how do you use one of these things? You know it's going to perform these steps, so how best do you set up your motor design processes to link into this and make use of it? Okay, so we've gone over what the algorithm looks like. Let's now wrap up a couple loose ends, and the first is on this business of constraints. And we, as you can imagine, we're going to need to be able to constrain our design space. We might have ranges that we allow our parameters to vary, so maybe our air gap is allowed to go between 0.5 millimeters and 3 millimeters, or maybe we know that the axial length of our machine can only be up to 100 millimeters. And so your algorithm is going to allow you to specify this, and you can specify the parameters or the constraints in two ways. The constraints can be placed on parameters. This is directly on this vector x. This vector x is what I labeled up here. This is our vector of parameters that define our design. And we can also place constraints on performance variables or performance calculations. And what's a performance metric or performance calculation? It's how your design performs. It's the outcome of your evaluation. So, for example, you might say that you have an objective of minimizing the size and another objective of minimizing the loss, but maybe you want to place a constraint on the amount of torque ripple. You might say that any design that has less than 50% torque ripple is okay by you, or any design that has torque ripple of less than 5% is okay. And the point is that you're constraining torque ripple, you're not optimizing it, and so you just want to limit which designs are acceptable by saying that this performance metric needs to lie within a certain range. And torque ripple is calculated as a function of your vector x. So you've evaluated that function using finite element analysis. But this constraint is not on the vector x itself, but rather it's on a function of the vector x. And objectives are all functions of the vector x. And we've talked about what objectives are in a previous video. So this can be, for example, trying to minimize loss or trying to minimize size. And so we're going to restrict ourselves to always having less than 3 objectives. And we can formulate our objectives in 2 ways. The first is that they can be the individual objectives that we've been describing. So, for example, that would be loss or size, or it could be torque ripple. Or they can be weighted sums of individual objectives. So this is part of the magic of how you can always restrict this down to 3 less than or equal to 3 objectives, because if you have more objectives, you can construct a single function that is a weighted sum of several objectives. And when you do this, you have to be very careful, because how you pick your weights for your weighted sum can change how that cumulative objective function is evaluated. And it's sometimes hard to come up with physical explanations for why you might choose a set of weights over another set of weights. So dollar cost of a motor design is naturally a weighted objective. And when I say dollar cost, I mean the cost of the active material. And so the active materials in our motor are our permanent magnets, our steel, and our copper. And so inherently, the total cost of our active materials is a weighted sum of the individual component cost, or the individual volume of our machine. So we can say that our copper cost is going to be the price of copper per meter cubed times the volume of copper, and the price of iron per meter cubed times the volume of our iron, and the price of permanent magnets per meter cubed times the volume of our permanent magnets. And so you can say that this is a weighted sum of objectives, of individual objectives, where the individual objectives are actually the volume of each of these materials: the volume of copper, the volume of iron, the volume of permanent magnets, and then the weights are the price of each of those materials. So in a way, this cost function is actually giving us an objective of minimizing size, because we're minimizing all of these volumes based on the weights, which are the prices. Okay, so let's summarize now. This video has introduced multi-objective optimization of AC machines. We've talked at a high level of the design process that we take when we optimize a machine, and how it starts from a design specification, then goes to an initial design that we construct from analytic techniques. Then we go into our optimization algorithm, which performs iterative cycles of evaluating designs, revising designs, and reevaluating designs. We then talked about how our motor design space is a particularly challenging space to optimize, which makes it very difficult to use the traditional optimization algorithms. And so instead we're going to be using global search optimization algorithms, or population-based algorithms, which rely on a certain element of randomness to help us find our global minimums. And our approach to doing this is that we're going to define multiple objectives. We're going to use a population-based algorithm to search for the Pareto front. Then we will visualize the Pareto front and intelligently evaluate the trade-offs of picking one optimal design over another optimal design. Finally, we outline the steps of an optimization algorithm from the perspective of us being users of that optimization algorithm, and realizing that we're going to have to link in our motor design expertise when it comes to parameterizing our designs and evaluating our designs. And finally, we've talked about constraints on optimization and a little bit more context on the objectives that we use for our optimization.